I'm Vinicius Gomez, and we're going to be talking about when microservices met event sourcing. So both topics are definitely not new topics, but bridging them together can bring us some very interesting benefits. And for the last 2 years, my team has been working with this combination in order to build a services platform for a large financial organization. And we saw the benefits in practice. So my goal today is share with you some of the ideas and some design details and implementation details on how to build this architecture using microservices and event sourcing together. So I am a software developer at ThoughtWorks. I write about technology and software development on my blog, and you can also follow me on Twitter. I am from Brazil, and that's where my accent comes from. So this is just a quick agenda for the presentation today. We're going to be talking about the traditional microservices approach, and then I'm going to introduce some concepts around event sourcing. We're going to talk also about command query responsibility segregation, which is an idea that fits pretty well in the event sourcing idea. And finally, I'm planning to show you some implementation details and run a live demo towards the end and go to the conclusions. So I want to talk a little bit about the traditional approach and then contrast that with the microservices together with event sourcing approach. So for that, I believe a good way is to define an example. So let's think about an online restaurant. That's a pretty simple data model. We have a menu with multiple menu items. We have customers with delivery addresses, and the customers can place orders with menu items. In the traditional microservices approach, we can implement that by defining 3 separate services, one for the menu, one for the customers, and one for orders. They serve HTTP APIs for users, and they communicate with each other using HTTP internally as well. So when a user wants to open an order, the user will send an HTTP post request to the orders service, and then orders will have to fetch customer information from customers in order to fulfill the user request. Pretty simple. Now, when the user wants to add a menu item, again, a post request to orders will fetch information from menu, comes back with a response, and then fulfill the final response to the user. So this approach has, of course, some benefits. It's quite simple. It's based on HTTP, so most technologies are able to handle HTTP protocol pretty well. And given a resource in our application, there's only a limited number of things we can do with that, given the HTTP methods. So it's pretty simple, I would say, cheap to maintain. But there are some challenges as well associated with this approach. First one is coupling. When we want to exchange information between services, they need to know about each other. At least if I depend on another service, I need to explicitly know how to reach that service and how to handle the responses. Resilience is another problem here. Imagine that our menu service goes down. There's no way for us to add items to an existing order. So that's another problem. Sometimes when we have too many internal HTTP requests going on to fulfill a single user request, that starts to become, to impact the user response in terms of performance. Also, the user intent of the traditional approach using HTTP is not always the best. There's some sort of impedance mismatch between what you want to do and the way we implement the functionality. Like, for instance, add item to order as opposed to post request to orders/UID/items. And most importantly, in my opinion, would be the ability of the traditional approach to handle only the current state, only the most recent state of the application. That's a restriction in order for us to have insights about what happened before we reach that state. There's no way for us to track user behavior or to know how we end up in that particular state at the moment. And that brings us to event sourcing. So let's see how ideas behind event sourcing can help us to minimize some of those challenges. So the central concept on event sourcing is the domain event, which is pretty much an arbitrary data structure that represents something that happened in the past. There are two very important properties on domain events. They are immutable. You never change a domain event after you store it, and they're immortal. You never remove it from the event store. So they usually have a payload with meaningful data for the domain and some metadata that helps us to retrieve it and to sort it. And once we have the domain events, we also have an event store in which we save our events in order. So this is usually an append-only special data storage that can provide us the whole history of what happened in our application. So once we have the event store full of events stored in a sequential way, for us to do anything meaningful in our application, we need to be able to rebuild the current state of the application. And that is done using the aggregates. Aggregates is a domain-driven design concept that in event sourcing plays a very important role. That represents the current state of the application given the events that are stored in the event store. So I believe a good way to exemplify that is by running an example. So let's imagine that we have an event store in our example domain with a few events in it. And let's say that we have an initial data structure representing the aggregate. So now when we fetch the events from the event store, we're going to apply one by one in order. And the result will be a transformation on the initial data structure. So the first event we have in the event store now is the order open event. And after we apply that in the data structure, we're going to have an ID, a status is open, and an empty list of items. After we have an item added to order event, that will cause the structure to have one item added to the list. We have another item added to order event. Now we have two items, and now we remove one of the items by applying item removed from another event. We add another item to the order again. And finally, we have an order placed event that changes the status of the order from open to placed. So imagine how powerful this concept is. Imagine the amount of business questions we can answer when you can track exactly what happened before we reach the current state. We know exactly what the user did for us to reach that point in time. That can be useful in many different ways, from analytics to fraud detection, and even for debugging the application. All right, so we have the domain events, we have the event store, we have aggregates that represent the application of all the events. But how do we create new events in the system? That's done by commands. So commands, they represent changes in an event sourcing system. They represent the user intent of changing some data. And they can cause new events to be created. So what we usually have is a user creating commands or sending commands to the application. the application will handle that command, and inside that handle procedure, what is going to really happen is that we're going to rebuild the state of the aggregate. The aggregate will handle that command and perform some business logic and business validations. And depending on the result, we're going to publish new events, or we're going to return back an error. So the idea behind commands is that they should be more meaningful than HTTP methods in order to represent rich domain interactions. So let's see this example, for instance, add item to order command. So a command name is usually in an imperative tense because it represents something that user wants to do. If we compare that with a post request to order /UID /items, you can see that the command name gives us a lot more insights on what's going to happen than the actual HTTP request. But still, when you have a REST-based API exposed through HTTP, how do clients send commands to our application, right? This is still an open question. I haven't seen any good way of doing that out there. But there are basically two options that I know of so far. One is to define a resource collection as a sub-resource of a given resource that's meaningful to our domain, which exposes us a way to send new commands through post requests. So when you have a /commands resource, we know that you can send multiple commands to that, and we can add the command type in the request body, as like type, for instance. That is pretty similar to the Redux actions for the ones who are familiar with JavaScript. So that's easy to implement on the server side, but that requires our clients to know about all the possible commands they can send as a type. Another option, and that's actually the option that my team has been using so far, is to define command URIs. So every command will have a unique URI in the system. And by convention, clients know that they can send posts requests to command URIs using just a regular request body. So that becomes pretty flexible because we can serve for every resource in our application. We can serve what are the available commands for that particular resource. For instance, for this order items collection resource, when we get the /commands, we can see that there's a link to one particular command, which is add. So another example would be the available commands for a particular order. We can add delivery address. We can cancel the order. We can place a new order. So that becomes really useful for clients because they don't need to build the URLs for the commands. They don't need to know what commands are available, and they can pretty much dynamically discover what they can do with a given resource, which is not just post, put, get, or delete, right? It can be whenever it comes back from the commands request. All right, we saw that we can send commands to create new events in the system. We can store those events in the event store. We can have the event store being used to rebuild the state of the application with the aggregates. But how do we perform queries in this application, right? In this world of event sourcing? The event store is usually not a good source for queries. We cannot perform joins, and you cannot perform any complex type of queries in the event store. It's really good for storing events sequentially, but not for retrieving information. And besides that, most applications, especially in domains like banking, we have a lot more reads than writes. So users, usually they check their a credit card statement, a balance, a lot more times than they make payments, for instance. So that becomes a problem for us since the event store is not a good it's not a good data storage for search. And that brings us to command query responsibility segregation, or SecureS. So SecureS tells us that our application can be divided into data models. One is the command model, and another one is the query model. Command model is a write-only model in which the user will send commands, and this model is connected to the event store, and we will store the result of the commands as events, and then publish that to an event bus. In the query side, we have an API which is read-only. The users cannot send any post requests or changes from the using the query API. And the query data model is pretty much optimized for search, and it's connected to a query storage, which can be a totally separate and different storage than the event store. We can have like a document database or a key value database or anything that matters for the domain. And the way that the query storage is updated is by having listeners around it that will be connected to the event bus. And every time a meaningful event comes, we would update the data in the query storage. So the data flow in this type of application goes in a circle, right? So users, they send commands from the command model, and that ends up being an event in the event bus. That will be picked up from the query model. The query model will be updated, and that data will be served to the user. So let's imagine that we have multiple SecureS applications in our architecture. How do they communicate with each other? The short answer would be they don't communicate directly with each other anymore. They do it from the event bus. So if one application is interested in data on the other application, that first application needs to have event listener in place in the query side, so that every time the other application publishes an event, the application which is interested in that event will be able to pick up that event and update the query storage accordingly. So there's actually no need for the applications to know about each other, no need for the services to communicate directly, and it doesn't really matter who is publishing an event. If I am interested in an event, the only thing I need to do is be able to deserialize that from the event bus and use it on my own query model. So the things that we have in the command model in a SecureS application are all the command definitions, all the events definitions that for the events that belong to that particular application. We have usually one aggregate. We try to model our services around one aggregate, which represents bounded context. We usually have an aggregate repository, which is the component responsible for fetching all the events from the event store and applying them to an initial data structure and rebuilding the state of the application. And a write-only API that accepts post requests with the commands. On the query model, we have events listeners that will be listening to interesting events from the event bus and updating the query model. We're going to have all the query entities, which are just denormalized data structures optimized for search. We're going to have repositories to serve that data and a read-only API. All right. I would like now to show you a little bit of a sample implementation of that, and using our example online restaurant. And hopefully those concepts that we just saw, they're going to be clear in the implementation. All right. So in our online restaurant, every service will be a SecureS application. We're going to have a command API, which serves like an HTTP API, accepting post requests, a query API, accepting GET requests. We're going to have an aggregate and an event store connected to an event bus. And on the query side, we're going to have entities connected to a query database and listeners connected to the event bus. So we still have the three services from the traditional approach: the orders service, the menu service, and the customers service. Now they don't need to know about each other anymore. They just connect to an event bus. Each one of them is a CQRS application, and internally they are identical in structure. So interesting things that will happen, and you will see in the when we have everything up and running. So the menu service will publish menu item added event to the event bus, and the orders service will have a listener for that event. So we're going to see that every time we add a new item to the menu, let's imagine that we are this restaurant staff and we are adding new items to the menu. We're going to see that those items will be automatically propagated to the orders service. The same happens with the customer sign-up event and address added event from the customer service. That will be automatically propagated to the order service from the event bus. All right, so I'm going to show you some running applications now and a bit of code. I'm using Java 8 here and Spring Boot to build the applications. I'm also using the Axon framework. Axon framework is responsible for providing us all the abstractions to deal with event sourcing and CQRS. It's pretty handy. It saves us a lot of time on writing that code. On the query side, we're going to use Spring Data REST. Since the query side doesn't have any meaningful business logic, all the logic is executed on the command side, we can just have Spring Data repositories serving data as HTTP controllers directly. And I use RabbitMQ as the event bus. All right, I'm going to disconnect from here. And can you see anything on the screen? Probably not, right? I'll try to increase the font size here as much as I can. So I don't have any Docker containers or VMs running here, just because it's just easier to debug everything running on my local machine. So I have here the three services running. In the first tab, we have the menu service. Next, we have customers and orders. And what I'm going to do now, I'm going to send some requests to each one of them. I hope the live demo gods help me this afternoon. All right. So here's the menu service. As you can see, we have an empty list of items. The same for customers. We have an empty list of customers and our orders. So our goal here is to open a new order and add an item to it. So first, let's create some menu items. So as you can see, one of the links we have here in this resource is the commands link. So that brings us all the possible commands that we can use against this particular resource. And there's only one, just add. So I have some sample requests already set up here. Okay, so what I'm gonna do here, I'm gonna send a post request to menu items commands adds. That's the command URI we just saw with some response body, request body. That contains description of the item and the price. So I'm gonna create 4 items. It's gonna be online Indian restaurant. All right, so by convention, each of these requests is returning a link to the entity being created. Since the command execution is asynchronous, that link might not be available yet, and that's something that the client code needs to be aware of. But at this point, with this low traffic we have, everything is there already. So we send the commands. We can see now that the query side is updated. We can see our entities here. And something interesting I showed you before is that the orders service is listening to these events on the menu side. So in the logs here, you can see that menu item added event was handled 4 times for each of the items you created on the menu side, and this is the order service. So as you can see, the events got propagated to this side. So here in orders, we still don't have any orders. Well, now let's create a customer. So first, to create a customer, actually, we first need to see what are the commands available to this particular customer's resource. And we can find that by navigating to the commands link. And that tells us that we have a single command available, which is sign up. So let's send a post request to sign up. I already have some post requests here set up. So we're going to be sending a post request to customer/command/signup. That's the command URI with some request body. We only require the email. And we're going to be also adding addresses, a couple of delivery addresses to this customer. And we're actually going to create 2 customers. So when we run this, we expect the query side of customers be updated, as well as orders should listen to that event and update the query side accordingly. So here you can see the links to the customers created and the addresses. And if we navigate back here, that should be available already in the customers resource collection. All right, we have 2 new customers added. And if we check the logs on orders, we can see a couple of customer sign up event and another one here, and as well as address added event. So that means that global consistency is already taken care of. So one interesting thing here, since we have this resource here, let's say this customer, we can see that there is a commands link in it, and we can see that we can do things with this customer. We can change the email, and we can verify. And the same thing for menu items as well. Modify, remove. So that comes back to that particular way of exposing commands as URIs. That becomes pretty useful for client applications to dynamically find out what are the commands available for each of the resources we are dealing with. All right. Let's now finalize our demo here by opening an order. think I already have open order here. All right, this is going to open a new order by sending a post request to orders commands open, and also send the request body with the customer. And that's it. If we access this link, we're going to see that there's this order. There's no items in it yet because the order items is empty. But if we come here and in the order items necessary resource, we can see that there are commands available here. We can add a new item and so on and so forth. I think at this point, you pretty much got the idea. So next, I would like to show you some of the code structure for us to implement that thing. It's probably going to be very, very small. You cannot see it, right? Yeah, let me try the presentation mode. All right, thanks. So I guess this is a little bit better. So this is the order service. So as you can see, we have two main packages, the command and the query packages that are representing the command and the query models from CQRS. Since the events are shared between command and query, we have a separate package for the events, which belong to this particular domain. And the data flow is quite simple. As you can see, we have another package here, which is the API. The orders command controller is just exposing an API for us to send commands to the orders resource. And what that does, I'm going to show you just a code snippet here. All right, IntelliJ is getting crazy right now. So I was going to show you that the controller will handle the request body, and we'll create a new command object and send that to a command gateway. And after that, that will be picked up by the aggregate, and then events will be published. And that's the flow for the command side. Unfortunately, I think we cannot see it here. Let's try to toggle presentation mode again here. There you go. So in this particular controller, this is the place where we create a new command. Let me see if I can show you the place in which we create the event. So we have an order aggregate that handles that command we just created, open order command, and that's going to apply an order opened event. There is a correspondent listener for that in the query side. If we navigate to the query side, there's a listener for order open event. Yeah, presentation mode didn't work quite well here. But what it does is pretty much it picks up the event, creates a new order representation in the query side, and saves it to a read-only database. And that's going to be served in the query API, which is served by Spring Data automatically from the repository for us. Yes, I will make all the code available in GitHub, as well as the presentation later on. And if you want to see more details or discuss about the implementation, you can go to the ThoughtWorks booth afterwards or tomorrow. I'm going to be there, so we can talk about it. Yeah, I hope you were able to get some idea on the implementation. But if you wanna see more details, please go there to the ThoughtWorks booth later. Yeah, that's it for the demo. So you saw this is pretty feasible. All those ideas are pretty not hard to implement given the technology we have available today, especially in the JVM space. And I think we're going to be able to draw some conclusions right now. So the combination between microservices and event sourcing provides us some very interesting benefits. As you saw, event sourcing provides us a way for performing history-based queries, because we save everything that happened in the past. We have every event representing in a small granularity the user behavior and everything that happened. So we can perform very interesting type of queries. For instance, how many times an item is removed from an order? How many times our order is how many times an order was canceled without any item added to it? Stuff like that. Event sourcing also provides us audit log by design. So audit log is a requirement for many domains, like the banking domain has this requirement quite heavily. And we don't need to implement anything else other than having the event store to already have these available to us, which is pretty handy. Immutability is another advantage we have in event sourcing. Since everything that we care about are the events that are stored in the event store, and they are immutable and they cannot be removed. So we can pretty much scale that horizontally in a safe way, because there's no mutable state to compete. The user intent is usually better represented when you use commands as opposed to HTTP methods to represent changes in your application. And also, our services in this architecture are pretty much decoupled. They don't actually need to know about the existence of each other. If you want to replace one service with another service, or if you want to change the source of who is sending event X to the bus, that's pretty much irrelevant for the consumers of a given event. So there's no direct communication between events anymore. And resilience. As you saw in our example, as soon as we add a new item to the menu, the order service listens to that in the bus and updates the query side. So if something happens in the menu service goes down, we can still add items to existing orders. We can still open orders. We can still place orders until the other service is down. So this is a pretty useful capability of this architecture. But there are some challenges as well. Of course, this architecture is definitely more complex than the traditional approach. There are more moving parts. There are more components to maintain. There are actually more code to write and maintain. And that's a direct financial cost to our team. Another challenge is the amount of events. So if you accumulate so many events that the rebuilding of the current state of the application becomes slower, we need to manage snapshots to store intermediate states of the aggregate and then apply only the events on top of it. and that's another cost we need to maintain. Also, since the event store is immutable, there's no way for us to perform database migrations if an event structure changes. So one way of dealing with that is by writing event upcasters, which are pretty much mapping functions that will act on old version of the events and transform them to the newer versions. And as we have more and more upcasters, that also becomes a little bit harder to maintain and test. Race conditions are a problem as well. A few times we see that we cannot guarantee in which order events will be published to the event bus. So consumers of those events, they need to provide code to deal with this kind of situation. Event contracts are another problem. Every time we change the structure of one event we manage in our particular service, if service B and service C depend on that event, we need to make sure that we respect the contract, or we change the consumers in order for them to not to break. And also eventual consistency. Since everything happens asynchronously, we send a command and pretty much forget about the result. There's no guarantee that problems won't happen in the event bus and the listening of that particular event will be delayed, and that can cause impact on client applications. And client applications must be aware of that, and they have to deal with requests and responses a bit differently than they do in the traditional approach. Well, so evaluating those challenges and the benefits is something that whoever is considering using event sourcing and microservices together have to go about with their teams. But from my past experience of 2 years working with this kind of architecture in my team, we can safely say that the benefits they overcome the challenges, and they provide us a lot of very interesting possibilities in the way we provide value to our customers, our business nowadays. So that it's pretty much it. If you have any questions, you can ask now, or we can talk later about this on the ThoughtWorks booth. This is not the only talk about event sourcing and microservices and event-driven architecture in this conference. Tomorrow we're going to have Maria Gomez and Stacy Waterall talking about pretty much the same topic, but from a DevOps perspective. We used to work together in the same team. And also Karum is going to be talking about the same topic, but from the perspective of systems integration. So yeah, that's it. Thank you.